Okay, so today we will start learning about these state space models. So this is actually the last lecture, and as announced before, next week, today is 16, this is Wednesday, this is Monday, and next week, this is Monday, this is Wednesday, and this is the remaining classes. Okay, so here we have quiz 2. Okay, next Monday we have quiz 2, and spanning these 2 lectures, we will learn about state space models and actually the Mamba. Okay, this is the new architecture. I mean, people, the computer vision researchers are gradually getting interested in this new architecture, whose name is Mamba. So yeah, actually, we are expecting that this could be next architecture. To the transformer. Okay. And next Wednesday we don't have any class. So, and spanning these 2 lectures, we will do final presentation. Okay. So this is the actually last, schedules. Okay. And this Mamba will be, the state space models will be the last lectures. Okay. So we already learned about the transformer. Okay. So maybe you may be familiar with this figure. Okay. So the transformer that is composed of the encoder and decoder, and their main operation is the self-attention mechanism. Okay. Actually, in quiz 2, this is very important content. Okay. So another thing regarding the quiz 2 is open book quiz, same as before, but you don't able to bring the electronic devices. So no electronic device allowed. Okay, only paper materials are allowed. Okay? And the quiz 2 will be 1 hour actually. Okay. Okay. And also the range of this quiz 2 will be from the lecture 1 through lecture 9. Okay. Okay. But I mean, we will maybe focus on the lecture after quiz 1, but some of the contents could be come from this lecture 1. Anyways, so it will contain some of the content in lecture 9. Okay. So I believe that you are already familiar with this transformer, and if you are not, then please refer the video recorded. Okay. And we also learned about this DETR, which is the object detection pipeline. Okay. So using the transformer, we can actually extend it towards the object detection task, and that is called as the DETR. But actually, I missed one of the transformer architecture whose name is VIT. So this is more, live architecture that can exploit the transformer architecture in the context of computer vision. But actually, I missed this. Sorry about that. But I think, yeah, we have to know about that before explaining the Mamba. Okay, so I include that here. Okay, so and VIT, you have to remember that this VIT is having just transformers encoder architecture. So it does not have decoder. It only have the encoder architecture. And it is almost similar to, its operation is almost similar to that of the transformers applied in the text domain. Okay. And VIT, that is abbreviation for Vision Transformer. Okay. So DETR, that is having both encoder and decoder. And each operation is a little bit far from the transformers applied in text domain. Actually, it loses some of the sequential information, especially for queries. Okay, but I mean VIT, because it is not using decoder, it is more simple actually compared to the DETR, and it can be trivially applied to the image domain by just changing some of the input format. Okay, so the name of the paper that proposes the VIT, the paper name is like this. So image is words, 16 by 16 words. So what it actually does is given one image, it make some patches from the whole image by dividing the whole images into some of the patches. Okay, and then it supply those patches as the token for the transformers encoder. Okay, so previously in DTR, we involve the CNN architecture and first extract some of the image feature that is one-dimensional vector and apply positional encoding, and then apply this feature instead of the raw images as the input to the transformer encoder. But in VIT, what we do is we just divide the images into patches, and each patch becomes the input to the transformer encoder. Okay. But of course, before supplying these patches into the transformer encoder, we apply some linear operation, which is the WX plus B. Okay, W and B is the weight we have to train. Okay. Anyways, we transform the image patches once. Okay. And apply some position encoding. So here, because we are dealing with the 2D images, there are 2D positions for that patches. So we encode such position information as the positional encoding. And at the same time, we have to supply one more input to the transformer encoder's input. So that's the class, we call that as the class token. So this is the class token. So we are, if there are P patches, if there are P patches from the obtained from the image, then we actually supply P plus 1 number of tokens to the transformers encoder. The one is reserved for this class token. Okay, so you already know that the transformers output, their number of output for transformers encoder, that's actually same as the number of input. Okay, so maybe these patch features are actually updated. Okay, in the transformer encoder, they are updated. Okay, and also this class token will be also updated by by applying the self attention to other patch features. Okay, this will be also updated. Okay, and we will not use these updated patch features. Okay, we will disregard these updated patch features, but only will use this updated class token. And we will map that using the MLP to the real class probability. Okay, so in that purpose, we need this class token. Okay, so we don't for the image classification, we don't need any updated features for the patches. So we will disregard this, but we'll only use this specific token whose name is class token. and further map that to class probability. So this is how we will use the VIT for the image classification task. And inside the transformer, if you magnify the transformer encoder, then that looks like this. Okay. So here we have the self-attention. Okay. And this is the input embedded patches with the position applied, positional embedding applied patch features, and apply some normalization and apply self-attention, and then further map that to the updated features using the MAP. That will be outputted here, okay? But we will disregard most of them and use only the class token, their updated values, okay? And further map that to class probability. So this is VIT, okay? And I mean, for the object detection task, that actually predict the bounding box and their corresponding probability. Because of their complexity, we need decoder and other specific loss functions called as the Hungarian matching. But here, VIT, that's because, I mean, thanks to the simple characteristic of the image classification, this VIT, that is very actually trivial to understand. Okay, and this is the actually the formula for I mean indicated for this. Okay, so actually this is the input. Okay, we apply positional embedding, and XP is the how to say the feature for each patch. Okay, first patch is feature, second patch is feature, and there are actually n patches. And we apply some positional embedding or the transformation for each patch. Okay, and we have another token whose name is class token. So this is our input to the transformer encoder. And then we apply this kind of operation, which is the normalization and multi-head attention, okay? Multi-scale attention, maybe MSA. And we apply MLP multiple times. So this is actually, this kind of architectures are applied multiple times, L times, okay, for the intermediate responses. And at last, we apply another normalization and predict the output. Okay, so this is the VIT, their encoder. Okay. But one of the problem in this VIT was that, but in general, transformer, their weaknesses is if there are n patches, then their self-attention, their complexity is order n scale. Okay, we have to apply the dense cross-dot producting between the input patches. Okay, so if there are n number of input tokens, then our self-attention will exhibit this kind of time complexity. So that's actually weaknesses for the transformer. So there have been some, I mean, attempt to improve the performance, especially for the, I mean, speed of the transformer. And this twin transformer is for that. And actually, the other, I mean, variation for this VIT is this D-date is another improved version of the transformer. So we will learn about that before learning about SSM. So swing transformer, I mean, this is swing means shifted window. That is swing. Okay, so we will apply this kind of shifted window scheme. Actually, before that, we will apply the window scheme to the certain images to reduce the number of n, because their attention mechanisms complexity is order n square. So if we can reduce the number of input, then we can greatly reduce their time complexity. So for that, this twin transformer is wanting to reduce the number of tokens for the transformer, okay? So using the window, for example, this is the original image. They are using this type of window, and then they will apply self-attention only for the patches inside this window, okay? So, I mean, inside this window, there will be a few patches, okay? And the idea of swing transformer is they will apply self-attention in between the patches coming from these windows, small windows, okay? So by doing that, actually, we can greatly reduce the time complexity, but the problem was, of course, because of that, the patches in this window cannot see the patches coming from this window, for example. So it loses some good characteristic of the transformer, okay? So transformer is exhibit heavy complexity, but it can understand some of the global context inherent in the images, okay? It densely attend to other patches globally, so it can be, robust. Okay, that's the good characteristic of the transformer. But actually, if we use this kind of window, then that will actually lose such good characteristics. So what authors try to further propose to further deal with such problem, they propose some more schemes. And first thing is they are using the hierarchical or multi-scale windows. So they are using this type of multi-scale windows, okay, to relieve such problems. Okay, another important scheme to use to further solve this problem, they use shifted window. Okay, so what it does is first time, even with the same scale window, in the certain layer, they will divide the images in this manner, okay? But in the next layer, even with the same size window, they can divide images by shifting the windows to this, okay? So this is important. This is trivial but effective. So, I mean, they are actually shifting this window maybe by 2 pixels, and now the windows looks like this. Okay, so actually that is this. Okay, so this is the shifted window scheme. Okay, and the authors are insisting that this kind of shifted window that can be helpful for propagating some of the information, for example, here to the the pixels in the far windows, okay? So using this kind of shifted window scheme, spanning multiple layers, they can propagate some of the information accumulated in this window to different windows, okay? Are you guys following this? And the swing transformer, this is one module, okay? This kind of layer, that is one layer. And swing transformer, that is actually having multiple swing transformer blocks, okay? So they are involving multiple blocks that divide the overall images into window and apply the self-attention using the window. They apply that with multiple times, okay? And with the multi-scales, okay? That is the swing transformer. So using original attention, multi-scale attention mechanism, this is the time complexity for that. So actually, if the image size is H and W, then if the image size becomes bigger, then the time complexity exponentially increased. But when using this window attention, then this term loses the square for width and height, but instead having m square. M is the number of window in the images. So this is, better than the original attention. So it greatly reduced the time complexity. Okay. So anyways, this is the swing transformer that can optimize the speed of the transformer. And it shows similar or, better performance, even better performance than the original transformer. So people are using more frequently using this swing transformer. And another important problem of the transformer is it does not have any inductive bias. Okay, this is also very important thing, when choosing the architecture. So inductive bias is roughly same as you can understand this term as the prior, okay, prior knowledge. Okay. When we have the prior knowledge, the training becomes a lot easier. So if you have, humans also sometimes learn about new knowledge, okay? If you have some prior knowledge, for example, if you have some experience in this computer vision class, then you can learn more easily than others, okay? So this inductive bias is like that. So if the system, the architecture is inherently having some prior for some domain or not, okay? For example, the CNN and recurrent neural network, convolution operation is applied for if they are applied to the image domain, they roll as some of the filter, okay, for processing the images. So they have some locality bias, okay, when processing the images, okay. Actually, they are actually suitable for processing images, okay. So convolution operation is more suitable for images. That kind of thing is called as inductive bias, okay. And recurrent RNN network, they can process the sequential data. Okay, that kind of thing is inductive bias. Okay, RNN is mostly applied to the sequential data, and CNN, those are applied to the image domains. Okay, that kind of things are some prior knowledge or inductive bias. Okay, so CNN that can be easily or trivially trained for the image domain, and RNN that can be easily adapted to the any sequential data. But RNN sometimes suffer when applied to, for example, image domain or others. Okay, so fully connected layer, but fully connected layer, which is the MLP, okay, or the graph network that have some inductive biases, but they are, less compared to the convolutional CNNs or RNNs, okay? So, and also the inductive biases of the transformer is, less than convolutional network or the RNN, but it has more inductive bias than the the MLPs. Okay, so we can say transformer that have not much prior knowledges on domains. For example, when applied to the vision domain, it has less prior knowledge compared to the convolutional operation. Okay, so we can think that it may take more effort to train the transformers if they are applied to the vision domain. Once they are properly trained, transformer, they can be better than CNN in terms of the performance or accuracy. But during the training, they can be, they can be more non-trivial to, train using the vision data, okay, because of the less inductive bias. We can say like that, okay. So one approach that tackle this kind of issue is the date, okay. So they relieve this problem by using some of the distillation. So they have this CNN network as the teacher. I think most of you are already familiar with distillation. So there are teacher and student, and we, enforce the teacher's knowledge to student, okay? And also at the same time, apply the standard cross entropy laws for the student, okay? When training the student, we actually use two signals as the supervision. One is the original cross entropy laws. This is standard one, plus another teacher by, teacher output. They are, how to say, closing the teacher network's output and using some L2 laws, which is the mean square error laws, to student output to be close to this teacher output. That's distillation. Okay. So here, this is the VIT architecture, and this is the patch token, which is the patch. Each patches the features. Okay. So from the image, I already told that we supply each patch as the input to the transformer encoder in VIT. So these squares are denoting the patch features, which is called as patch token. And this is the class token that I explained when explaining the VIT. And they actually have another token whose name is distillation token. Okay. And this is the VIT, their transformer encoder architecture. And mostly composed of the self-attention and the MLP layers. Okay, this is the VIT architecture, which is composed of transformer encoder and MLPs. Okay, and then we will estimate some output. Okay, and for the class token, their updated value, we will apply the cross entropy laws, same as the VIT. But here, for the updated token from the distillation token, we will apply the distillation laws. Okay? Distillation laws, that is simple, actually L2 laws between our output and the teacher's output. Okay, we are actually try to follow the teacher's output for our output. Okay. And teacher network is the CNN architecture. That has some inductive bias because the VIT, it is non-trivial to train. Okay, it takes some more time compared to the CNN because of the inductive bias. This paper, the authors are experimenting that when we supply some of the distillation laws to our architecture based on the transformer, then they want to confirm that the training could be faster than before. Okay, and the result is very interesting. By involving one more token, okay, and apply this kind of distillation laws. This is the training epochs, okay, and this shows the performance. This is the accuracy. When we do not apply any distillation, and this is different types of, distillation. Uh, Anyways, these graphs are showing the accuracy when applied with distillation. Okay. Then, compared to the no distillation, the performance is getting better even for few ample result. Okay. So, that's the merit of distillation, and actually it exhibits that transformer indeed, does not have much inductive bias compared to the CNN, and on purpose supplying the inductive bias or some knowledge from the CNN when training the transformer is actually helpful. Okay, so we can see that. Okay, and also they are saying that actually there are some hard distillation and soft distillation, but they are saying when applied with hard distillation, it is more effective, and low distillation, the accuracy is like this. Okay. Anyways, this is showing that transformer is exhibiting less inductive bias, and supplying CNNs as the teacher and doing the distillation can relieve such things. Okay, that's the day. And day and swing transformer, that's very famous nowadays. Okay, and then we will learn about this state space model that is called as SSMs, actually. So we already learned about this RNN, CNN, and transformer. Okay, those architectures are actually improved to capture some long dependencies. Okay, so RNN, the naive RNN suffers from this, suffers to capture long dependencies. So there have been LSTMs, okay? So they explicitly control which information to lose, forget, or which information to accumulate, okay? And also transformer, that is so far the best architecture that can capture some long dependencies between the input, okay? So because inherently transformer can capture some global context, okay, via the self-attention, they can be good for capturing the long dependencies. However, they still suffer capturing the very, very, very long dependencies. So the paper say that more than this number of this number of dependencies, long dependencies, they are suffering. So SSMs are, some paper already proved that the SSMs can be useful and promising to capture such very long dependencies. So, the SSMs, the state space models are actually denoting this kind of thing. Okay, so, and Y is CX plus DU. So here, what U means is the input. U is the input. And X is hidden layer. And Y is the output. And this X dot means differentiation. Okay. Differentiation to time. Okay. That's X dot. And they are saying that when this A matrix is properly set, this SSM can be very good model that can capture long dependencies. That's already known in some paper. Okay. But the problem is it is very hard to, the computation memory requirements for the real implementation. So matrix A, implementing the matrix A that can capture long dependency, that can be very computationally heavy, so it cannot be actually implemented. Okay, so when a matrix is properly set, they can capture long-range dependencies, but it's not very efficient. Okay, so that was actually the hurdle for implementing or applying this SSM architecture to the real problem. But in ICLR 22, there have been some architecture that can solve this kind of, that can actually solve the complexity issue and make these things feasible, implemented in the hardware. Okay, so their algorithm is called as structured state space model. Okay, and what they are doing is actually this. So this is the continuous time SSMs. Okay, as I mentioned, original SSMs, they are assuming that this U, the input, and the hidden state and others are, and also the output, those are the continuous time signals, okay? Which means the signals like this is the continuous time signal, okay? But when used during the, inside the deep architectures, we normally use the discretized input, and also we are using some discretized output. Okay, so the author for this paper is saying that we can sample some of the signals to make this UK, which is the discretized input. Okay, so this is the offset. Okay, and K is some interval. Okay, and UK is the how to say, the sampled input. Okay, and also this differentiation can be just the, when it is discretized. When it is discretized, the differentiation also could be like this. Okay, just the time, the difference between the consecutive signals can be the differentiation in discretized signals. So, and also the A matrix, B matrix, and others, those continuous matrix also have to be like this to sample some continuous matrices. Okay. Anyways, I will not go details with this kind of formula, but I will just provide some high level induction for these formulas. Okay. So anyways, they want to first sample the continuous time SSMs to make them as the discrete time signals. Okay, so now SK, the hidden state, becomes also the discretized, and also the final output become discretized. And also they omit this D because this is actually the trivial thing when solving this kind of differential equation. So they actually omit this part, okay? But because this could be trivially added to the final solution, so they actually omit this part, okay? And next, they, by making the overall formula with, converting that into the discretized version, and what they did next is they actually find, they actually calculate the output for each K one by one. Okay, so when calculating this X0, you need to apply k is 0 to this formula, then you can find that when x minus 1 is 0, this term goes 0, so this term only remain. Okay, and then using the next one, you can get this y0. Okay, and when you can also next calculate x1, y1 by using this result. Okay, I mean you can apply k is equal to 1 to this formula and can find that actually x1 could be obtained by this and y1 could be obtained by what? By this formula. Okay, so you can calculate one by one like this. Okay, so I mean these signals x1, y1 and x2, y2, x3, y3 that can be sequentially calculated like this. Okay, and you can actually have this kind of general solution for yk. Okay, this is the sum of the general solution for yk. Okay, and you can actually make it this kind of operation when can be this kind of formula can be simplified as the convolution operation like this. So this mu u is the input signal. So that comes here for entire input signal. And that can be interpreted as applying some filter kernel and apply some convolution operation on the input signal. And that convolution filter is actually having these values. Okay. So one way to calculate the overall hidden state and output values is calculating them sequentially. Okay, but it takes a lot of time. Okay, it may take a lot of time, but we can actually parallelize this process by applying one filter kernel on the input signal. So, I mean, but this kind of interpretation is the contribution of this paper, and actually, they can make this whole process more efficient. Okay, so this structured SSM, they provide fast way to calculate these state space models, okay, by discretizing the original continuous time signals. So originally, the signals are continuous, but in this paper, they are discretizing by sampling some of the values from the overall continuous functions. They made that as the discretized state space model and also interpret their output as the convolution using this K kernel. Okay. And by doing this, they can accelerate the calculation of the SSMs. Okay. And then after that, I will continue this maybe this Wednesday. These SSMs are the fundamental theory for this Mamba. Okay, Mamba is just adding some selection mechanism on these S4 models. Okay, so this is actually denoting the discrete time SSMs. This figure is actually there are A matrix, B matrix, and C matrix. And this is the hidden. Previously, we denoted as X. Hidden was denoted as X, but this paper is denoting it as H. And instead of U, which is the input, they are using X. Okay. And without this part, the figure overall same as they are denoting these discretized SSMs, but they involve one more module that can select some of the parameters. Actually, they are selecting B matrix and C metrics and some, offsets, okay? And to make the output more robust, they are using some selective mechanism. That is actually the Mamba architecture. And then actually there have been some recent work that try to involve this Mamba architecture for many vision tasks. So, we will learn about that in the next lecture, okay? So this is end of today's lecture and see you this Wednesday, okay? Thank you.